All right, it's 8 p.m. somewhere in London or in Greenwich. So I welcome everybody to our VSA webinar. And today I have a pleasure welcoming Michael Furlong from the University of Waterloo. So without any further delay, Michael, the floor is yours.
Thank you. It's great to be here. So today I'm going to talk about how we implemented Bayesian optimization using vector symbolic architectures, and how that let us do that in a more efficient way than you might normally. So this is work, I should say this work is generously supported in part by a gift from the Intel neuromorphic research community, and it's being conducted in the Neurocognitive Computing Lab. So Jeff Orchard is the PI of this project. I'm Michael Furlong, I'm a postdoc, working with Nicole Dumont, who is a PhD student at the University of Waterloo, and she is doing some exciting work on neural SLAM, using these vector symbolic representations. And she's going to be giving a VSA talk on June 6th. So that should be very interesting. And of course, Terry Stewart at Waterloo, currently at the National Research Council of Canada. So before I was at Waterloo, so it's just a little bit of background from where I'm coming from. And I understand that this is, a community of very in-depth VSA researchers, and I'm more new to the field. So prior to being at Waterloo, I was working at the Intelligent Robotics Group at NASA Ames, and I worked in field robotics and autonomous science. And that was my graduate training and my background. And so these are just some of the robots that I worked on while I was there. This is sort of the setting and the context of getting robots to do science on behalf of people, or on behalf of scientists who are people, when they can't necessarily communicate with the scientists reliably. So the outline of this talk is, first, I'm going to try and pitch you on this notion that autonomous science is interesting, a compelling problem, and it also motivates the use of vector symbolic architectures, and also through vector symbolic architectures, neuromorphic computers. Then I'm going to sort of very briefly cover VSA's fractional binding, and then what aspects of that we're using to implement the efficient Bayesian optimization, and then I'm going to cover the meat of the subject itself. So let's start with what autonomous science is. I think there's a lot of different ways you could describe it, but at its heart, it's about taking actions to learn about functions, or at least that's how I think about it. So you might have some state space here, x1, x2, or action space, x1, x2, and you have some function defined over the action space. And in this case, it's a constant function, so it doesn't change with time. There may be some measurement noise, observation noise, some variability in the system, but if you sample at any one point in the action space or the input space or the domain of the function, you should get the same or similar results every time. There might also be time varying functions, right? So this could be things like the activity of microbes as a result of the day-night cycle, right? There could be some periodicity to it, or it could be that there is apologies for the siren. It could be that there is no periodicity; it's just a changing function, and we need to explore it and learn as much as we can. And then you could also have random functions, which might be, say, we could be talking about ejecta plumes from the surface of Europa, right? So all of a sudden, all this material shoots out, and you want to observe it, but you don't know necessarily where it's going to happen. So the state space here could be, the surface of the planetary body. You don't know when and where it's going to happen. It's happening randomly, but you want to learn more about this random process, the distribution that generates it. And so again, autonomous science is all about figuring out what to do, getting a robot to let itself figure out what to do, to learn about what these functions are like. which is just an interesting intellectual challenge at the very least. I would argue also has some pragmatic benefits. Specifically, especially in my work in planetary exploration, we will often have precursor data from remote sensing when we go to investigate a planet. And so this terrain here looks like, it's interesting. It's got some dark spots. It's got some light spots. We want to go, travel all over this place and figure out what it's like. And so we take the remote data and we plan a trajectory. But what happens then is we actually get to the surface and we find it's a lot different than we anticipated, right? So there'd be this deep crag here, or these spiky regions here become difficult to navigate. So you want autonomous science because you're always going to have better data on the ground, or if not always, the majority of the time. So we want these machines to be able to make these decisions on the surface, specifically when, the robot can't call home and ask a human for help, right? If we're on, the visible side of the moon, this might not be such a problem. It can get reasonably good bandwidth up and down. But if you're in a lava tube, or if you're under ice in a subsurface ocean of Europa, you can't reliably communicate with the robot. The robot needs to be able to make its own decisions, and we want it to be able to make decisions that maximize the scientific return of the mission. And so there's, from an autonomy perspective, there's sort of two classes of things that go into the robot. The first would be just sort of your standard autonomy to enable science missions. And so this would be your sense, plan, act cycle. So this would be building a map, planning a trajectory, determining how to safely navigate across a particular part of terrain, scheduling operations for the day. But then there's the autonomy that's specifically about conducting scientific inquiry. And that's where we're having robots making decisions about what observations to collect. It needs to have ways to infer or generate hypotheses or update beliefs in previous hypotheses. And then it also has to select experiments that it wants to conduct in order to falsify the hypotheses, which will produce observations, and this cycle sort of continues. And now there's some blurring of the line between these two classes, and planning algorithms for finding a route, and then planning algorithms for scheduling your experiments. I mean, these can be, if not fundamentally, at an abstract level, they can be the same kinds of algorithms. But we also are dealing with, specifically collecting information for information's sake, or reward, or where the objective is not necessarily as concrete as planning a trajectory. But in either case, these problems are hard. They can be challenging problems to solve, complex problems to solve, even when they're not on another planet. And when we get into planetary exploration, this is compounded by the fact that planetary science, autonomous planetary science, is constrained. And then two of the ways that they're constrained is in the size, weight, and power of equipment that can go on board a vehicle. And then, I guess I should say that, when we're talking about planetary rovers, the power budget for computing can be 5 watts, 10 watts, that kind of a ballpark. There are also dynamics and time constraints of these missions, right? So if you are in an entry, descent, and landing part of a mission, you're hurtling towards the surface at speed, you need to make decisions quickly and effectively. If you are driving a vehicle at speed across a loose, unconsolidated material like gravel or sand, you need to make smart decisions that incorporate the dynamics of the vehicle. Similarly, if you might have a very slow-moving vehicle, but you are operating on the surface of the moon, and your vehicle is not designed to survive lunar night. So if that's the case, you have a 2-week window of time in which to conduct all your operations before the sun sets on you. The temperature drops to minus 150 centigrade or something, and the camera lenses all break and the battery explodes, or whatever happens. So there are very real constraints on these systems that motivate having low power and having sophisticated autonomy that can execute in a reasonable period of time. Now, space-rated computing, these would be your rad-tolerant, your rad-hard computers. They've been designed to fit into these size, weight, and power constraints, and they certainly do the job. And from the dynamics or time constraints point of view, I'm going to say, yes and no. Yes, in the sense that these are sort of the workhorse systems that are engaged in control in high-speed operations, right? I mean, like these are the systems that are being used in missions today, and they are meeting those requirements that are placed on the vehicles. However, if we wanted to put some really cutting-edge algorithms, these are not the computers to do that, right? By virtue of what needs to be done to make the machine rad tolerant, and also I think by virtue of it being sort of a niche computing market, the state of the art in space computing lags terrestrial state of the art by about 20, 30 years, that kind of a time frame, right? So we're not necessarily going to be running a ResNet 50 on this computer at frame rate. On the other hand, we have state of the art CPUs and GPUs, which do not meet the size, weight, and power constraints, or broadly don't. And if they do, they don't necessarily, they haven't been radiation hardened. I have a graphics card that its max power consumption is greater than the power budget of the robot that I worked on in my PhD. So this is almost, a non-starter. That said, they're great for doing, these are the state of the art. These are the fastest things we have that can run these algorithms at speed. And they're the kind of behavior and performance that we want to start putting into these robots. I will point out that, one solution to this is to have, your data center at some remote distance. And if you have a high bandwidth, radio connection or otherwise to the robot, then these kinds of computing, they can be workable. But once we start getting into, the long distances that we have, to Mars, to Europa, further beyond, having this kind of a tether, even if it's not a physical tether, starts becoming less plausible. And for that reason, we want to put the smarts on board the robot. And that is why neuromorphic computing is interesting to me, because it promises to be low power, which is very important, and it also promises to be fast. And if these promises pay out, then this could be a key enabling technology for many kinds of autonomous operations, including planetary exploration. There is a problem, though. How do you program a neuromorphic computer? And I think that's something that people are still figuring out. For standard computers, we have, at the conceptual level, we can write down our ideas in Python. We can then translate that to machine code, and then we run it on the hardware. These are well-established principles. And I say Python because I like Python. It could be C in a compiler, whatever you prefer. And the way that I've been thinking about it is that, at our conceptual level, we have vector symbolic architectures. And here I'm showing my bias to the work that's been done at the University of Waterloo, where I'm currently positioned. But of course, obviously, there are many fine researchers in this area who've been using these systems to bridge the gap between symbolic and connectionist models. And then we can use things like the neural engineering framework to make this connection between the symbolic and the actual implementation. And then we need some hardware to run it on. And of course, neuromorphic computing, which, is certainly seems like it's gaining traction and momentum. In the case, the Loihi is a great example, then provide us the substrate on which to run these algorithms. At least that's the hope. So before I move on, I guess what I want to say is that this is the motivation, that there are many other hard autonomy problems. These are the autonomy problems that I work with. There is a challenge, especially in constrained environments, to execute sophisticated autonomy. and I say constraint, I mean constraint in terms of power and time. Neuromorphic computing promises to alleviate some of these constraints and mitigate these constraints. And it's vector symbolic architectures that I think will help us figure out how to program these systems. So with that said, I'm going to move on to how we're representing data in fractional binding, which I suspect is going to be old hat to many people in the audience. But basically, what are vector symbolic architectures? They map symbols to high-dimensional vectors, hopefully in a space where if the symbols encoded are the same, then the similarity is high. I've encoded high as 1, low as 0. And of course, if they're different, then we should expect the similarity to be low. We have these standard operations: similarity, bundling, binding, unbinding, which, similarity answers the question, how similar is A to B? Binding creates a new symbol that bears similarity to its constituent parts. Binding creates a new symbol where the symbol does not necessarily bear similarity, under the similarity metric to its constituent parts. And then unbinding can undo the work of binding. And then I guess I've been working with the holographic reduced representations VSA. I've been working with the semantic pointer architecture from Chris's lab. And of course, specifically, we're using dot product for similarity, vector addition is similarity, circular convolution for binding, and then unbinding is circular correlation and dilution, or more pragmatically in the implementation, binding with the pseudo inverse of the encoded vector. And again, we can use these vector symbolic architectures to represent structured data, like a sentence. So subject Andy are bound together. Or rather, we can see the sentence as a bag or a bundle of bound objects where the subject is Andy, the verb is 8, the object is cereal. And then if we want to query who the subject of the sentence was, we simply unbind the key subject and make it Andy as the result. We can also represent numbers. We can use iterated binding to represent integers. So if we have some mapping of 1 to a vector that we'll call, 1, O-N-E, to represent 2, we could bind it with itself. To get 3, we'd bind 2 with 1, which would be 1 and 1 and 1. And so the question then is there a mapping from the number 3, the integer 3, to the encoding 3 that is consistent with the scheme? There is. It is literally iterated binding, which we can also do in the Fourier space. And of course, there are the Fourier holographic reduced representations, which don't convert in and out of Fourier spaces. And then, of course, what we can also do is extend this to real numbers, real value data. So it's the same techniques. So we have this initially randomly selected vector, which we call the axis vector. We take the Fourier transform, we do element-wise exponentiation, and then we take the inverse Fourier transform back out, and that gives us our vector representation. And of course, if we want to do it for vector value data, we just do the fractional binding for each element of the vector, and we bind those together. Excuse me. And then just to sort of dig into the guts of the fractional binding, and I guess I should say I sort of alternate back and forth between fractional binding and spatial semantic pointers. Spatial semantic pointers, of course, being the language that we've developed at the group here in Waterloo. But the way it works is that this, one of the ways we can implement this is that the Fourier transform of the axis vector ends up being a vector of complex exponentials of basically this phase matrix theta. And so theta is randomly selected, generated where the elements are drawn from the uniform distribution over negative pi to pi. This is predominantly the representation that I've been working with, and this, of course, has the effect of projecting these data points onto the surface of a high-dimensional sphere, represented in 3 dimensions here for visualization purposes. But then something else interesting happens when we take this data and we've encoded it using this particular representation, is that when we take the dot product, we get a kernel like object, or I should say a quasi-kernel. And in this case, and this is proved by Aaron Vogler, if we have two vectors x and y, the similarity metric between these two vectors is, if it was one-dimensional, it's just the sink of the distance between the elements, and of course, if it's n-dimensional, it's the product of the sink, which is, the sine of x over x. And there's this wavy function here. We also, I suppressed this for most of the talk, but we also have a length scale, which can be an element-wise division of this distance measure. And I guess I should point out that we call this a quasi-kernel because this value can become negative. And so that violates some of the assumptions about kernel functions when we're talking about kernel function theory. And then Frady et al. Showed in 2021 that there is a fundamental connection between this fractional binding representation and a technique from machine learning called random Fourier features, where depending on the distribution that we use to generate the phase elements, we get a different similarity kernel when we take the dot product between two fractionally bound values. So this is the uniform distribution that we're using. We get a sinc kernel out. If you use a triangle distribution, then you get a sinc squared function. If you do Gaussian, you get Gaussian, and so you can play these games to get the similarity kernel that you need. And I guess you can also do sort of additive kernels through concatenations of representations of VSAs, but we won't have to go into that right now. But what this shows is that there is a connection, a fundamental connection between this representation that I guess derived from cognitive science, between that and machine learning techniques, specifically techniques that allow us to take kernel functions and map them to linear functions, which is a very useful way to improve computational efficiency, and that is the trick that I'll be taking advantage of in this talk. The other thing I'd like to highlight, and so this is some work that's been done by Nicole as part of her PhD thesis, is that if you choose the phase elements in a specific way, you can start getting similarity measures that look like the grid cell activities that we see in the hippocampus. And so again, this is a very powerful thing from my perspective. Again, speaking to the VSA community, I'm sure that you're well acquainted with these concepts, but we have this convergence between machine learning techniques and observations in biology that sort of derive from using this representation from cognitive science. And that is, at least for me, it was very exciting, and I thought it was very cool. And I think it's a very powerful tool and technique. So finally, let me get to the meat of what I came to talk about today, and that is specifically using this fact that we can get this nice kernel similarity out of dot product of fractionally bound representations to implement an efficient Bayesian optimization. So again, to step back to this notion of planetary exploration, we need a mechanism to for the robot to figure out where it should go next, what action it should take next, or what point in the state space. So we have some true function that is defined over a domain. In this case, it's a two-dimensional domain, and it could quite literally be, the XY coordinates of places on a region of terrain you're trying to navigate. It could be more abstract concepts. And these black crosses that are popping up is where the algorithm that we've implemented is saying we should sample next. And we're particularly doing Bayesian optimization, which means it's trying to find a maxima, could be a minima, but we use a maxima in the function, and it ends up clustering the sample points in this region predominantly. So the objective that is used to drive this exploration, a common objective that's used to drive this exploration, I should say, is mutual information. And to do that, you're trying to compute, there are many mutual informations. There are many information gains that we can talk about. I'm working with Shannon information and expected information gain. But the point is that we have, we're trying to learn something about the function that represented by these parameters theta. And we want to know, assuming we take this action X and we have some belief distribution about the observations we get it from taking action X, how much that changes or reduces our uncertainty in these parameters. And the way you can do that is you have some estimate of the mean value of the function for every point in space, and then you have some measure of uncertainty in the what you're predicting in the function value at all these points in space, and you combine them together to give you an acquisition function, and then every point you take a sample that maximizes the acquisition function or as best as you're able. The question then becomes, where do we get this mean variance from? Gaussian processes are a convenient tool and a commonly used tool to provide this, but they can become computationally intensive. At least your standard vanilla Gaussian processes, the complexity and memory requirements grows with the number of samples you've collected. What we did is we used fractional binding, and then we used Bayesian linear regression, a linear model, to approximate a Gaussian process while improving memory and time complexity. So the algorithm itself is here. What I think I'd like you to pay most attention to is this line, which is the acquisition function we're maximizing, which is to say we use our model to get our estimated mean or our functions that estimate mean and variance at every point in the function domain, and then we combine them by summing the mean with this term here, which stands in for the mutual information or the expected information gain, and so it's the square root of this term gamma plus the uncertainty minus the gamma. And then once we select the point, we update gamma with this uncertainty measure of the sample point that we collected. And just so we understand what that term is doing, is as we collect more data, gamma will grow. And the larger gamma is, the less of an influence the variance, the uncertainty here, has on the selection point. So what this is this is a term that initially favors exploration, but as we explore and as we've collected more information about the world, we then downweight the importance of exploration. And you might view this as a way that's sort of dealing with the uncertainty versus variability trade-off, which is to say, at the beginning, we are both uncertain. We're uncertain about the observations we're collecting, and we don't know how to attribute much of it to variability or how much to attribute to the fact that we just haven't collected enough sample points. If you are sampling a variable process, and you've collected thousands or hundreds of thousands of samples, and you've well estimated the variance, it's no longer useful to keep plugging away at sampling that region, because yes, it is variable, but it's also well understood to be variable, and so you want to drive to other regions and then gain information there, instead of just resampling the thing that you know is variable. Now, with this particular framework that we're discussing here, that trade-off is going to be happening globally. So it's over time, we are confident everywhere, and that downweighting uncertainty everywhere will be downweighted. But that is what this term is doing. So again, Gaussian processes are not the only place to get mean and variance. So their standard approach, we have some distribution over a model at every point in the space. Another approach, and again, these have computational problems. Another approach that is regaining interest is using occupancy grids, and different, more efficient implementations of information gain, where you divide up the world, you plop down a distribution in every grid in the world, and you figure actions, select actions that maximize the information gain, and you can improve computational efficiency by having this this discrete space to search through, instead of having to search over the continuum. That said, with Gaussian process regression, And this is where the computational complexity comes in. We have a bunch of data points. Our mean and variance are defined by our kernel function in our data set. And the problem really comes in from this covariance matrix here. I've denoted it C. But the size of this matrix is square root of the number of data points that you've collected. And then if you want to invert it, then it's about cubed in the number of data points that you collected. So this term T here. And that grows without bound. There are techniques for sparsifying Gaussian processes. I would suggest that they might also be problematic to fit on low constrained computing resources, but I'm happy to have that discussion. But it is a well-known trick that we can approximate these Gaussian processes if we have a feature representation that induces a kernel under the dot product. And so what we're seeing here is a Gaussian process fit with our SSP representation. So this is inducing the sync function. And so as you can see, you're getting similar results. The edges are different. The behavior of the edges, where we don't have data, is different. This is using a radial basis function. This is using a sync function. So we would anticipate that there would be some differences. But where we get the benefit is in this covariance matrix here that we use for the Bayesian linear regression. The size of this is fixed in the number of sample points. It is square of the dimension of your feature representation. And so when we never pay an additional penalty for long-term operations. One of the other benefits of this particular setup is that if we're having rank 1 updates, and we just collect one observation at a time, we can update the inverse directly, and so we never actually have to invert the matrix, which can allow for a slightly more efficient online operation. But this is the trick, right? So we're approximating a Gaussian process. We're using this feature representation, and this is how we get the computational efficiency. That, of course, comes at a cost, but it is more efficient. So we tested this. So I coded up the Bayesian optimization algorithm. We tested it on a number of test functions, but there are 3: the Himmelpfeil, the Brandon Hu, and the Goldstein Price. They're all standard optimization targets. The code, if you want to play with it, is available online at github.com /ctn_waterloo SSP Bayes_opt. These slides will be shared after the talk, and that link is active, so you'll be able to get it if you'd like. And then we measured the performance of the algorithm by looking at the average cumulative regret. And so regret, of course, is the difference between how well you did and how well you could have done if you knew the best answer. At least that's the version of regret we're using. And what we see here is we tested 2 versions of the mutual information sampling algorithm, one using the randomly selected SSPs, one using the hexagonal SSPs that are modeling grid cells. And then we used a Gaussian process that is just using, this is actually using the kernel that is induced by this sync function here. And what we see is that the performance is fairly similar. It's at 30 trials, we see that the random one is doing slightly better, but they're all kind of converging to the same point with space. I don't want to big up any differences in performance here. What I want to show is the time, or what I want to highlight is the time to compute the query for where we should sample next. And with the Gaussian process, we see that it is constantly growing, and with the SSP mutual information, that term is constant. And Brandon Hu, again, we're getting similar performances, and then Goldstein Price, similar performance again. But it's this graph here. What this means to me is we can stick this algorithm in a robot. We can send it off, to the bottom of the ocean, to some other planet, and we can come back in 20, 40, however many years, and whatever else has gone wrong, it will not have run out of memory. and that is something that was enabled by using this representation from vector symbolic architectures. And we can see, doing an analysis of the using a Gaussian process, using an occupancy grid, or using SSPs. Again, a Gaussian process, it grows with the number of samples, square in the cube. With the occupancy grid, the complexity to compute the query and the memory to maintain the system is in the number of points you have in your grid. And so there is a trade-off, I think. I mean, between all of these things, there is a trade-off. I mean, like if we look at this graph closely, if you're collecting fewer than, I think this is about 10 samples, the Gaussian process approach is actually the better approach to use. But for long-term operations, I would suggest the VSA approach. And then there's also a trade-off to ask, with the occupancy grid, how big is the space? What is the right resolution? Does this need to be variable resolution? Does this need to grow? We could ask the same thing with the SSP-NI. We can represent, if we look at the hexagonal SSPs or the grid cell representations, eventually if you're covering enough territory, you'll need bigger and bigger scales, and that might need to grow. But there's discussion to be asked in practical situations, which is the best one. I have a bias. You'll be surprised to learn. But at the very least, we're looking at something that can operate for long term relative to the standard approach. And before I go to the next slide, I guess the objection. But a sensible response to this is, great, you've rediscovered random Fourier features. Fantastic. And I'll say, yes, thank you, I have. But it's a little bit more than that, I think. So with random Fourier features, at least as I've used them, you're representing data points. And one thing we can notice with this SSP representation, the VSA representation, we're taking this objective function, right? This is the thing that we're trying to maximize, and then we're converting it into, this is using the Bayes linear regression. We're searching through this vector space, not through the space of X, and then we decode the vector back into X, and then this becomes a convex optimization that we can compute. But more importantly, we're just dealing with vectors represented by vector symbolic architecture, and they can represent complex structures. We've talked about sentences, and so one of the things we wanted to look at is, well, what if instead of figuring out the next sample point, the next sample point, the next sample point, could we select trajectories, entire trajectories instantaneously? So this is ongoing work. This is being done with Rikan Tanova, who's a postdoctoral fellow at Stanford University. And what we're trying to do here is seeing if we can do Bayesian optimization in the space of trajectories, where what we get out of the optimization is a vector, a VSA vector, that we then decode out the points in the trajectory. We follow the trajectory, we see how well it performs. And to make this work, we need to have a sensible similarity measure between vectors, between trajectories that are represented as vectors. So we've done some preliminary experiments where we have, this blue trajectory is the target trajectory, the orange trajectory is the distractor trajectory, and we vary, this green trajectory varies from one to the other smoothly with this parameter alpha. So when alpha is 0, this end of the graph, the green trajectory is the blue trajectory, and when alpha is 1, this end of the graph, the green trajectory is equal to the orange trajectory. So we encode the trajectory as a bundle of 3-dimensional data points, which is the XY position and the time, the point along the graph, along the trajectory. And we just sum those up. We create this new vector zeta, and we take the dot product between blue and wherever the green line is. And that gives us this curve where we see, well, alpha is close to 0, that is to say the green line is dominated by the contributions from the blue line, and we're doing this smooth transformation. The similarity is quite high, and then it drops off, and we get sort of this random noise out here in the extreme. But what this says to me is that, certainly within the neighborhood of this line, we can measure similarity. And if we can measure similarity, then we can make predictions based on it. We can use this Bayes linear regression trick. And then we can also control the width of this bump by changing the length scale that I mentioned a while ago, but have been mostly suppressing for this talk. And so with, as the length scale gets smaller and smaller and smaller, this bump gets narrower and narrower and narrower. And I guess we shouldn't be too surprised at that, because, if our kernel is a sink of a distance divided by a length scale, as that length scale goes to 0, then the sink function should start approximating a Dirac function. And so we can sort of, we see this here, we're picking out at alpha equals 0, the trajectory, and then everything else is noise. And this is again, is interesting to me for two reasons. One, we're being able to do similarity over these more complex data structures, which is doing analogical based reasoning. I understand is one of the main reasons that VSAs were developed. But the other thing is, when I showed you those graphs of the plot of the Gaussian process predicting a field over some lunar terrain, and then we have the grid cell representation over the terrain. The computational benefit of the grid cell representation comes from assuming independence between the grids, right? And there's points between the Gaussian process where every point in space affects every other point in space. And the grid representation where everything's independent, you can have sort of neighborhoods that inform other cells in the grid. And what's nice about this representation, by changing the length scale, we can actually finely tune, or not finely tune, but we can at least tune the influence of neighboring regions, which I think is pretty nifty. Right, so I think that basically sums up what I wanted to present today. So we're doing mutual information exploration, which is a useful technique in automating exploration in planetary robotics. I mean, it's useful in automating any kind of sort of exploratory operations. It could be drug discovery. It could be playing hide and seek. But we did it using these representations that are at least our lab, others I'm sure, have been using to represent neural state. And then we also didn't need to learn these representations, which is very handy. And we can use this to reason about more complex data structures, and what we're hoping we'll show is that we can use this to actually select high value parts from the space. It's a principled information theoretic algorithm with substantial improvements in time and memory complexity, which means it's applicable to long-term duration robots. And again, it comes from using these techniques from the VSA. And the places we're hoping to take it next, mapping it to Loihi's neuromorphic hardware. We also want to connect it up with the SLAM representations that Nicole is using in her work, because ideally we would have sort of a unified exploratory robot using VSA representations. And the other thing we want to work with is seeing if we can inject any constraints in SSP space that might make for constraint optimization a little bit easier with no additional cost is what we're hoping. So just like to thank the people who've sponsored this work over the duration. And I'm happy to take any questions.
Thank you. Thank you, Michael, for the great talk. So questions, please.
Yeah, and I guess the first thing, sorry, just before the questions, it is, I am almost 100% certain that I have missed important results in VSAs, and I am very much looking forward to hearing those. So thank you in advance.
All right, Bruno.
Yeah. It's Fritz. We're all here
Hi,
together.
we're all here together. This is Fritz Sommer. Hi, Michael. Thanks for your talk.
I have a question concerning the exploration objective that you're using. So you're using this expected information gain, kind of this old Lindley approach. There is actually very interesting work in the more recent literature of other, other options, and I wonder if you have looked at those. So I mean, we had an option in a 2013 paper, that's Little and Sommer, which was is predicted information gain, which is very similar to your objective, but it basically optimizes the gain in the state space and not in the parameter space. And that actually worked for us better for exploring kind of environments. We use this for on an agent in very simple environments. And then there's other work by someone called Oudier. He's French, he's in Bordeaux, I think, and he uses an objective function which is called learning progress, which is not even information theory based and pretty quick to actually evaluate. And for that reason, might be also interesting for you. So anyway, I don't know if you know this stuff, but there's an entire field which is called kind of sequential optimal experimental design in statistics, which you should actually check out. That this is kind of, they are all interested in very similar questions that you are asking here.
Yeah, thank you. Definitely. I think so what you're seeing with this particular choice of objective is really a reflection of, I've been doing this sorry, I've been using this particular objective function to make the job, to do the job. And then when I realized I could do this representation with the SSPs, the fractional binding, it was like, oh, well, let's just use that. So I think, yeah, no, I'd be more than happy to explore any and all alternatives. Also, I mean, even like the Cauchy-Schwarz quadratic mutual information is another one that's more efficient. Well, more efficient than Shannon again.
Yeah, I think that might be promising to actually look at these different objectives for exploration. They make a big difference. That's at least what we have seen in experiments.
Sorry, you're saying making a big difference in terms of
learning a model quickly. Yeah, in terms of actually learning a good model quickly. Yeah.
Yeah. Okay. So the sample efficiency as opposed to the computational efficiency.
Yeah. Yeah. Exactly.
Or both. Okay. Cool.
Yeah. 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 Thanks.
Okay. Thank you, Fritz. Any more? Anybody else want to ask a question? Let's see. Well,
sorry, if I just may on this subject of alternate information measures. So the group that I'm familiar with, that this is Nathan Michael's group at Carnegie Mellon via Vijay Kumar's group, working with Cauchy-Schwarz quadratic mutual information. They, well, 2019, recent in pandemic time, published a model of using Gaussian mixture models to represent terrain and maps. And one of the things that I think would be interesting to plumb there is just like, how similar is that to a VSA representation? Because I think that might be an interesting avenue to pursue. And I guess one of the things that they pointed out in that paper is that with this compressed representation, they can save a lot of data transmitting over, back from space, where bandwidth can be quite limited. And the VSA representations that I used in this paper were, I think, 150 dimensional, which I could, definitely get down on less than a second from Mars, which is pretty good compression, I think.
So let's give another chance for the audience to ask questions. Okay, but well, as usually, I want to remind that I mean the direct communications are always an option. So if you have any questions to Michael, so please use either our mailing list or contact him directly. And from my side, I just want to say once again that I'm very happy that you presented at our seminar. So that was very exciting talk. Yeah. So that's it for today then. And we thank you, Michael, once again for joining us. And giving this
Thanks very much for having me. It's been great to be here.
Yes. And we see each other in 2 weeks from now. So thank you very much, all.
Thank you.
See you next time.
Thank you.
Yeah. Bye-bye.
Thank you.
And Michael, can you please share the slides with me that I can link them from the website?
Yeah, I'll shoot them over to you.
Yeah.
Just after this.
Okay. Thank you. Thank you. Bye.